There we go. Jeez, nothing is easy. What's going on here? Okay, everybody. So I am a hair behind getting reading quizzes out to you guys. I should have reading quizzes for chapter 13 and 14 out, probably 13 tonight, 14 tomorrow. I'm going to bump the deadline for chapter 14's homework all the way to next Monday to give you a little bit of extra time to get that done because I haven't got a reading quiz up yet. Our exam right now is scheduled for next Monday. I was wondering if anybody would have a big issue if we scheduled an exam on a not class day, because we don't really have classes per se anyway, we have recitations. So we could have our exam, for example, next Tuesday instead of next Monday. And that would give you guys Monday as a short class meeting to ask any last minute questions or do more practice. We have today scheduled as exam review time. We've covered most of chapter 14 already. But I'm happy to have a last minute review when you guys have finished up all the homework, like the day before the exam, to ask last minute questions. So is that, what does everybody think of that? Exam Monday versus Tuesday. The cool thing with the exams are you have any time during the day to take it. I'll open the exam at 9 in the morning and you'll have to have it finished before 11 o'clock at night. So you'll have like a 2-hour block somewhere in that time where you have to sit down and take your exam.
I have a quick question about that. Is it something that we print off, or is it like multiple choice like the reading quizzes?
So it's not going to be on Canvas. Oh God, no, that would be horrific. It'll be something that you either print or just you can take it on blank paper if you don't have print capability. So you could take it on blank paper. You don't have to write the questions down, just write your answers for each question down on blank paper, number them clearly. That would be fine. Or if you do have print capability, you can print it and it would be just like taking an in-class exam on paper.
Awesome, thank you.
So then you will use Cam Scanner or whatever app that you use to create your PDF files, take a picture of each page, turn all the pages into just one PDF file. So several students in the class, even though I have like remarked on their assignments, are continuing to submit a separate PDF for every page of their assignment. That is a huge pain in the keister for me. I can grade all of them, but I have to sort of keep track of deductions and points and like carry them over to the next file because I can't look at more than one file at once. So when you use Cam Scanner, use it to turn all of your pages into just one PDF file. Make one PDF file and turn it in, please. That makes my life so much easier. So grading one PDF file, let's say that takes 1 minute, it probably takes 3 minutes to grade 3 PDF files. Like it really does make a huge difference in terms of the time it takes for me to get through the class's grading. And considering that I have a pre-lab, a lab, normally a homework, and a check-in for 90 students to grade every week, it's like it takes a while, right? So, and then exams obviously are going to be quite a bit of grading as well. I'm not saying that that's my job totally, but if you guys can help me out, that's one way you can help me, and I would really appreciate it a lot. So I'm already spending like 12 hours a week just grading, which is gross. Okay, so does anybody have a mark for where we left off in terms of our discussion of chapter 14? I can't remember exactly where we stopped because it's been a while.
We went through some of the reactions and everything. That's
We went
pretty
through
much
reactions of just alcohols, right? That's kind of what I remember.
just some of the reactions, yeah.
Okay. So we're not going to talk too much at all about ethers other than how to name some very basic ones. There are no reactions that you guys have to know of ethers. Generally speaking, they're not very reactive anyway. They are very good solvents to use for organic chemistry. They're also good anesthetics. So diethyl ether a long time ago used to be used as an anesthetic, but it was prone to overdosing. Sometimes, like if you inhale a little too much of it, you just die instead of falling asleep, which is not great. So now there are anesthetics that are a little easier to dose. They're still ethers, but they're normally polyhalogenated ethers instead. So if you look back in the chapter 14 PowerPoint notes, you'll see pictures of some of them with lots of halogens attached and then an ether someplace in the middle. I'm just making notes for myself from class to make sure. Also, I will have a practice exam for you guys. I am in the middle of writing that. It is going to be basically like I'll look through some old exams that I've given for the exam 1 for Chem 131 and maybe take out a few questions that I would have a hard time rewriting and then just basically give you an old exam to look at. So you'll see a lot of the kinds of questions, the level of difficulty of questions that you would see on one of my real exams. The reading quiz kinds of questions are actually pretty similar in a lot of ways as well. So you'll see only on paper, there won't be any bugs with the reading quizzes or with the exam like there were the reading quizzes. So yeah, I can't miss, you know, I'm trying to give you guys instant feedback and Canvas is like just behaving exceedingly poorly so far. So let's hope that that gets better. Okay. That's not a bruise. That is ink on my hand. That is not a grievous wound. So don't mourn me. All right, I'm fine. All right, ethers. Remember that ethers have an oxygen bound to 2 carbon-based groups, okay? A total of 4 electron groups around that central atom. So the bonds to carbon counts as 2 electron groups, and then the 2 lone pairs count as 2 more. That gives ethers, in terms of their bond angle, an approximately 109.5 degree bond angle and a shape around oxygen of bent. Ethers tend to be polar, but not nearly as polar as something like an alcohol, all right? So we say polar because we know that oxygen is more electronegative than carbon is, all right? So if we add those 2 bond dipoles together, in general, unless there's something very specific about an ether that makes it nonpolar, normally you'll have a net dipole for the molecule pointing toward the oxygen of the ether, which means that the oxygen side of that molecule is slightly negative and the side with the carbon-based groups is slightly positive. So because of that, ethers have the medium kind of intermolecular forces. We call those dipole-dipole forces. So they attract one another more strongly than nonpolar molecules like hydrocarbons, but they attract each other less strongly than things like water that can do hydrogen bonding or alcohols that can do hydrogen bonding. So one of our long-term big takeaways from this class is that no matter what functional group we're talking about, the stronger the intermolecular forces that molecule with that functional group has, the higher the melting and boiling points for the molecule, all right? So that's assuming that we're talking about molecules that are roughly the same size as one another, because as molecules get bigger in molar mass, they also have larger and larger melting and boiling points. So if we were thinking about something like this, ethanol, all right, a 2-carbon alcohol versus dimethyl ether versus propane. All three of these are roughly the same size in terms of their molar mass. All right, very, very similar in size. But when we rank them in terms of their melting and boiling points, ethanol will have by far the highest melting and boiling points. And the reason why is because it has the strongest type of intermolecular forces. So the fact that it has an OH group allows it to hydrogen bond. Hydrogen bonding is our strongest kind of intermolecular forces. Now, even though it's polar, it's a special kind of polar because of that functional group where we have a hydrogen covalently bound to oxygen. That's what allows it to hydrogen bond. Ethers are polar also, but they're not capable of hydrogen bonding. They're only capable of having that second strongest kind of intermolecular forces, dipole-dipole forces. So we would rank the ether as number 2 in terms of melting and boiling point. All right, it would have a higher melting and boiling point than propane, but a much lower melting and boiling point than an alcohol would. Does that make sense to everybody? So you got to think about 2 things when you're trying to rank compounds in terms of their melting or boiling points. You have to think about what kind of intermolecular forces do they have, and then you have to think about how big they are. All right, so in this case, I took out the how big they are argument because they're all almost the exact same size. So if they're all the same size, then the stronger the intermolecular forces, the higher the melting and boiling point. All right. Now, we're not going to learn the IUPAC name scale or the naming system for ethers because most ethers that we're going to name for this class are exceedingly simple ones. So I'm going to teach you how to give common names to very simple ethers. So if we have 2 alkyl groups attached to an oxygen to make an ether, the common name just says that you name each one of the alkyl groups as a substituent and then say ether afterwards. So what if I had something like this? What 2 alkyl groups, what 2 alkyl substituent groups do I have attached to my oxygen here? Also remember, in bond line drawings, you can put in those 2 lone pairs or you can leave them out. You have to remember that they're there, right? That is not a linear oxygen. There are 4 electron groups on that oxygen, not 2. So I see a propyl substituent group and a butyl substituent group, right? 3-carbon substituent group, 4-carbon substituent group. So I'm going to name these in alphabetical order and then just say ether afterwards. So I will say that this is butyl propyl ether. Really simple to name, easy, not complex kinds of dialkyl ethers. Now, what if we have 2 of the same substituent group? In a situation like that, we just would say di and then whatever the alkyl substituent name was. So these are both propyl groups, so we would call this dipropyl ether. Any questions about that? So alkyl halides, another of the functional groups that we cover in chapter 14, very, very similar in polarity to ethers for a lot of the same reasons. So for example, if we have this molecule The only polar bond in this whole molecule is that carbon-chlorine bond here. Chlorine, having a higher electronegativity than carbon, gives us our bond dipole. So if that's the only dipole for this whole molecule, we would anticipate that the chlorine side of that molecule would be the slightly negative side, and the whole side with the carbon chain would be slightly positive. In other words, this alkyl halide, like most alkyl halides, is polar. All right. And because it is polar but not able to hydrogen bond, it has the same kind of intermolecular forces that ethers tend to have, which is dipole-dipole forces. All right. Now, there's one thing that I messed up and didn't talk about with ethers. I'm going to sneeze in a second, too.
Stare at the light.
What's that?
Stare at the light.
I tried to, but it was too late. Yeah, I know. I forget to do it sometimes. You know how your brain kind of turns off when you're about to sneeze? So very small ethers that are only a few carbons total big. All right. So I think the book may say like up to 5 or something. I don't care about an exact number because this isn't a memorization class, but there are times when small ethers are capable of dissolving in water. And the reason why is because think about what happens if we mix together. First of all, what would we name this ether right here?
Ethyl methyl ether.
Very good. So that's ethyl methyl ether. Now imagine if ethyl methyl ether was mixed together with water. What kind of intermolecular forces could be shared between molecules of water and molecules of ethyl methyl ether? That hydrogen on water is capable of doing hydrogen bonding. And we know that hydrogen bonding is what happens when a hydrogen with a covalent bond to oxygen or nitrogen or fluorine is attracted to an oxygen or a nitrogen or a fluorine on another molecule. So by definition, that intermolecular force, the force attracting ethyl methyl ether to water, is hydrogen bonding. So for very small ethers, because they can share hydrogen bonding kinds of intermolecular forces, that allows them to dissolve very efficiently in water. All right. Even diethyl ether, you can dissolve about 5 to 7%, depending on the temperature, of diethyl ether in water. All right. Smaller ethers than that are even more soluble in water. And that's why, because they can share hydrogen bonding interactions. So first of all, what would we name this ether? And then tell me whether you think it would be more or less soluble in water and why.
Dipentyl ether.
That's it. So would it be more or less soluble in water than ethyl methyl ether? And can you explain why? I think most of you could probably tell me the right answer to the first part, but I want you to be able to explain why as well.
I don't think it would be very soluble because of, well, obviously the amount of other carbons that are attached to the oxygen. There's not enough to hydrogen bond to completely dissolve it.
So would dipentyl ether still form hydrogen bonds with water?
Yes, just very weak ones because there's not very much for the hydrogen to attach to. I guess, in comparison in the amount of carbons that are attached.
So maybe you're trying to say that polarity requires looking at the molecule as a whole, not just one part, right? Okay, that's exactly right. Yes, we have to look at the molecule as a whole. And on the whole, we see two long non-polar hydrocarbon tails on that ether. So most of that ether is very non-polar. And because of that, it is very dissimilar from water, which is a very polar solvent. So remember, like dissolves like. These two are much more alike one another than dipentyl ether is like water. So we would expect dipentyl ether to not be very soluble in water at all. I also have to teach you how to name alkyl halides. Pretty simple. We name halogens as substituent groups. So a chlorine atom as a substituent group is a chloro group. A bromine atom as a substituent group is a bromo group. An iodine atom as a substituent group is an iodo group. So we pick the longest carbon chain that contains a halogen if we're naming an alkyl halide. We number to get to the halogen as soon as possible because that's our substituent group that is most important if we're talking about naming an alkyl halide. And then we give locants to it and any other substituent groups. All right, so it's really no different than naming any of the other kinds of hydrocarbons or alcohols that we've named so far. Just we have to know what to name these as substituent groups. So I want to give you guys one that's easy first, and then I'll give you one that's a little harder. How would we name that molecule?
Two ethyl cyclochlorohexane.
So we have to give both of these names as substituent groups. We're naming them both as substituent groups. And we would start our numbering on that cyclohexane ring at the chlorine because it's the more important of the substituent groups. All right. So something like this should have a name like 1-chloro-2-ethyl cyclohexane. Now remember, we still have to alphabetize. We did that correctly here because C is before E. But what if instead we had an iodine there? Then ethyl comes before iodo alphabetically. So we would have 2-ethyl, 1-iodo cyclohexane.
I thought if it was at like chlorine would be position 1 all the time if it's in a ring, right? If it's just that and another one, isn't that substituent group
we still have to
assumed number 1?
We still have to give locants if there's more than one substituent group on a cyclohexane ring. So the only times we don't give a locant is when there's only one substituent group on a cyclohexane or on any alkyl ring. That's when we don't give a locant.
Okay.
So what about this? How would we name this one? It's tricky. This is really tricky.
Whoa.
I know. Remember, we're naming this as an alkyl halide, which means first step, we find the longest continuous carbon chain that contains the halogen atom. So what is the longest carbon chain that contains the halogen atom? How long is it?
Okay.
It's 2 carbons long.
2 carbons. 1, 2. Remember, this carbon counts as part of the ring. So a carbon can only be in a ring or not in a ring. It can't be both. Which means we have to name this ring here as a substituent group. So the correct name for this compound would be 1-bromo, 1-cyclohexyl ethane. So basically ethane, a 2-carbon alkane with a bromine and a cyclohexane ring, both as substituent groups at carbon 1. Now, this one's not too bad. I don't like it. I'm going to make it not as bad. It'll look worse, but it's actually not worse. It's better. Can you guys name this one? So in this case, remember, we're naming bromine as a substituent group anyway. So it's no big deal to name this thing as an alkene that has a bromine substituent group on it. See if you can figure this one out. Since we're reviewing for exam 1, we're going to have to name some alkenes anyway. This will give us some practice at that.
Do we just say it when we got her? Should we wait for other people as well?
Just wait. Yeah, give people just a minute. So hopefully you're numbering from this direction because we get to our first substituent group sooner. Really, if we're talking about naming this as an alkene, we get to the alkene at carbon number 3, no matter which direction we name in, but we get to the other substituent groups faster if we number from the right, which is why numbering from the right is better. So our alkene starts at carbon number 3. We have substituent group bromine and a methyl substituent group, both at carbon number 2. Orlena, you want to give it a shot?
I got 2-bromo, 2-methylhexene.
So very close. So you said 2-bromo, 2-methyl.
You have to say 3
hexene.
3-hexene. Still very, very close, but not perfect. Here's why. I'm going to draw another compound that has this name, but is a different compound, which means that this can't be the right name.
It has trans in it, doesn't it?
It does. So this and this are not the same compound. Remember, we have to differentiate between double bonds where the 2 identical groups, in this case hydrogens, are on opposite sides of the carbon-carbon double bond versus a case where they would be on the same side of the carbon-carbon double bond. So the correct name for this one has to be trans. 2-bromo.
I was thinking about that before I did any of it, but I was like, no, because they're not the exact same on both sides. But now looking at it, yeah.
You do have 2 identical groups. Those hydrogens are identical on the 2 sides. So you have to differentiate between whether they're on opposite sides here or on the same side here. So trans, and this would be the cis isomer of the same thing. All right, let's name one more halide together and then move on to something different.
If the halogen was in the place of one of those hydrogens for the cis trans, would that impact having to name it cis or trans then?
Yes, but we're not going to name things like that. All right. So the only type of stereoisomers that you're ever going to have to name is to be able to differentiate cis from trans. Okay. So you could have something where maybe there are two methyl groups that are identical, that are either on the same or opposite sides. So it could be any group, not just a pair of hydrogens, although that's a very common set of things to have the same on the two carbons that have the double bond. But in order to have cis trans isomers, you have to have a pair of things attached to the carbon-carbon double bond on the two carbons that are identical to one another. And they have to be either on the same or opposite sides. All right. What do you guys think about that one? So I have that as 2-bromo 3,4-dichlorohexane.
I got the same too.
Sweet.
Nailed it.
Good. So we do have to learn a little bit of chemistry of a functional group called thiols. So thiols are a lot like alcohols, but with a sulfur instead of an oxygen. All right. So an alkyl group attached to an SH instead of an OH. Now that is a pretty significant difference because sulfur is not nearly as electronegative as oxygen, which means that this functional group, even though it would make a molecule polar, would not make it able to hydrogen bond. So thiols as a class of molecules tend to be polar, but they have dipole-dipole forces instead of hydrogen bonding. All right. There are a minority, a vocal minority of chemists that believe that this hydrogen that's attached to sulfur is one of those superhero hydrogens that is capable of hydrogen bonding. So the kinds of intermolecular forces that thiols have are, like, on average a little stronger than your average dipole-dipole forces, but they're not quite as strong as hydrogen bonding normally is. So some chemists, okay, let me put it this way. If you want to start a fist fight at the next National American Chemical Society meeting, go in there and then make a claim that thiols are capable of hydrogen bonding, and then sit back and like watch the sparks fly, because this is something that's very polarizing. That's a joke, by the way. Polarizing, get it? Haha, polarity. Or sorry, I'm not even a dad, but I got dad jokes for days. All right. So thiols, in my opinion, are not capable of hydrogen bonding. All right. They do dipole-dipole forces. They're a little stronger than your average dipole-dipole forces, but not nearly as strong as your traditional kind of hydrogen bonding. That's what the models tell me. One other noteworthy thing about them is that they smell absolutely disgusting. All right. So that like potent rotten egg smell, if you ever have smelled a gas leak, that is a small amount of thiol that is dosed in with natural gas to make it stink so that you can tell that you shouldn't light a match because you'll become an astronaut. All right. So skunk smell is mostly, I think, butane, thiol. All right. Low molecular weight thiols are incredibly stinky. It just awful. So I promised at last recitation to tell you a chemical way to help clean up skunk smell. All right. So if you have a thiol, one way to clean it off is just to rinse it away, and even water, because low molecular weight thiols are somewhat capable of dissolving in water. Rinsing with water helps some. There's something better that you can do. What if we had a way to turn the thiol into a different functional group that wasn't as stinky? Well, if you use an oxidizing agent, and pretty much any oxidizing agent works for this purpose, thiols are one of the easiest functional groups to oxidize. And you can take two of them and they end up doing an oxidation where we lose a sulfur hydrogen bond and replace it with a bond between those two sulfurs. We oxidize them to a disulfide. Disulfides tend to not be as smelly as thiols are. So if you've ever heard clean up your skunk smell with tomato juice, I think, I'm not positive about this, but I think it mostly works because the oxidation of thiols to disulfides is catalyzed in acidic conditions. It happens somewhat quicker. So since tomato juice is pretty acidic, that actually allows air, the oxygen in the air, to act as an oxidant to make this reaction go a little bit faster. There's an even better way to do it, though. You can use your own oxidizing agent, like, for example, hydrogen peroxide, the stuff in the brown bottle. So that 3% solution of hydrogen peroxide is great at oxidizing thiols to disulfides. So if you ever get sprayed by a skunk, you probably don't want to wash your hair with it too much because you'll like bleach your hair, you'll photo bleach your hair a little bit. But the rest of your body, you can make a little bath with soap and hydrogen peroxide. And that's one good way to sort of deodorize skunk stank.
Hydrogen peroxide is also really good. Like if you get like a bloody nose and you get it on your shirt, you can easily do it that way. Like get out the blood stain from that.
So similar thing, yeah. Give me just a second. My battery's about dead. I think my wife might have unplugged my computer.
I thought it was my computer.
I thought it was mine too.
I was like, what?
My computer's plugged in. Why is it low? Yeah. So you guys saw that notification?
Yes.
That's awesome. That's like when you're driving in the car and you hear a siren on the radio and you're like, am I getting pulled over? Now, the cool thing is that disulfides can be reduced back to thiols. All right. The classic reagent for doing this is called beta mercaptoethanol. So you will recognize it as ethanol that has a thiol group attached to it also. And this is the most common reducing agent for reducing disulfides back to thiols. So basically what happens is if you add enough of beta mercaptoethanol, remember that in oxidation and reduction, something always has to get oxidized when something else is reduced. we turn all of our beta-mercaptoethanol into its disulfide while we re-reduce our disulfide back to the thiol instead. So there are lots of other reducing agents that work for this purpose. Also, this one is nice because its structure is really small and easy to remember. I think the one that they use in perms for hair is called ammonium thioglycolate. So why am I worrying about teaching you about the oxidation and reduction chemistry of perms? Because that is the way that the hair is relaxed and then held in place. So if you look at the proteins that make up hair, one of the 20 amino acids in basically all proteins is called cysteine. And we're not going to learn about cysteine structure in total until we get to the biochemistry section of the class. But here is a picture of cysteine all by itself. So that is an amine group with an extra proton on it, which is why it has a plus charge. This is a carboxylic acid that has lost a proton, which is why it has a minus charge. So that's why we call cysteine an amino acid, because it has an amine functional group and a carboxylic acid functional group. It also happens to have a thiol functional group, which means that if you get two cysteines close enough to one another, they can form disulfide linkages. All right, so that's really important to the structure of proteins because it can take parts of proteins that are very far apart from one another and lock them next to one another with a covalent bond, right? That's a covalent bond that we get just by getting two cysteines close enough to one another. These covalent bonds are responsible for a lot of the three-dimensional structure that hair has. So if you were born with curly hair, that means that your disulfide bonds are a big part of what is keeping it curly. If you were born with straight hair, your straight hair is being kept straight. The structure of your straight hair is largely due to the rigidity of those disulfide bonds holding your hair together. So in a perm, here's what happens. At the beginning of the perm, let's say that we're doing the classic perm where we start out straight haired and end up curly haired. You can actually go either way. You can perm your hair straight if it's curly. All right.
What about if your hair is just wavy? Like if it's not curly and it's not straight?
You can reset the structure of your hair with a perm, no matter what it is. If you want a nice curl in your hair, you can do it with a perm. If you want to make your hair completely straight, you can do it with a perm. So basically, it's resetting the three-dimensional structure of your hair. And what happens is, at the beginning of the perm, your hair already has disulfide linkages that are causing it to be the shape that it is. You got to be really gentle with your hair after you do this because you have taken away a lot of its structure. It's easier to break when those disulfide linkages are all reduced. And the ammonium thioglycolate, the stuff that they use for the reduction step, is stinky. Not as bad as like skunk stink, but it's smelly. Anybody ever had a perm before? Can you speak to that? Stinky?
My mom used to get perms all the time, and it's pretty. It's up there.
Yeah, it stinks. So after that, we roll the hair onto rollers to sort of set it in place, all right? And what happens is if you bend that hair, then different cysteines are going to end up close to each other than were close to each other when the hair was straight. So when we treat that hair with an oxidizing agent, and it's normally like a dilute solution of hydrogen peroxide, what happens is we reform new disulfide bonds, but we reform them with the hair already in a curly position. And those new disulfide bonds that form are not the same ones that were formed when our hair was straight. So those disulfide bonds keep our hair in that curly shape even after it's out of the rollers.
So with that is like perms wear out after a little bit. So is it just like your hair's kind of going back to the normal thing, like the
Yeah,
linkages are
I've
coming
thought
back?
about that. I don't know why the perm wears out, because the hair doesn't all get replaced over that amount of time. Maybe people's normal, like the weight of their hair. So, okay, here's another thing, Orlina. Disulfide linkages can reduce and oxidize in air all by themselves. All right. So every so often, even in hair that's not being weighted down with anything, you have disulfide bonds in your hair right now that are breaking, and then other ones that are forming. It's kind of an equilibrium process. So over time, if your hair is too heavy and not maintaining its shape well enough all by itself, you'll lose some of those disulfide bonds and then form new ones that make your hair straighter than it was before. So that's probably how it's wearing out over time.
Would showering be a big part of that also, like with the H2O of it, with the
Nope,
hydrogen
I don't
bond?
think so. So that it's a covalent bond, and it's not a covalent bond that that is reactive to most kinds of chemical stimulus at all. So oxidizing agents can form disulfides, and reducing agents can get rid of them. But most other kinds of chemistry is not going to do a lot to disulfides, which is really important because disulfides are some of the most important covalent bonds that maintain the three-dimensional structure of all the proteins that we use to do our jobs biochemically. So if there were a lot of different reagents that we could take that would mess those up, that'd be really bad for our ability to like live, to function as any creature that has proteins uses disulfide bonds as an important part of their structure. So we're just sort of hacking that a little bit to like reshape the disulfide bonds in our hair when we do a perm. It's neat. But nobody's ever asked why the perm wears out after a while. I think it's probably just an equilibrium process where your hair naturally might be heavy enough that over time, the equilibrium would make your disulfide linkages tend toward you having straight hair anyway. You can go against that equilibrium by doing chemistry for a while, but if your hair is heavy enough, eventually you're going to equilibrate back to disulfide linkages that have straight hair for you.
Yeah, I was just wondering because like my mom, as I said, she would get her hair permed probably every 6 months or so.
So here's the other thing that now I'm really curious about. I'm wondering if somebody with curly hair got a perm to straighten it, if it would curl itself back up over time. So I honestly do not know. And I have to read a little bit about that now because I'm very curious.
Intrigued.
Yeah, I'm very intrigued about this.
There's a lot of like chemical products that people apply on to themselves as well to maintain the perfect curlet or the perfect straightness, either by chemical straighteners that are applied daily, as well as shampoos and conditioners and leave-in conditioners, blah, blah, blah.
So if they were applying reducing agents to their hair every day, I would bet their hair would probably fall out after a while. It could be that they're applying a very dilute reducing agent, which just reduces a very small number of those disulfide bonds every day. And that could be like the daily hair relaxer that you're putting in. So I honestly, I do not have a whole catalog of.
There's a secondary market for virgin hair that's not been treated or anything like that, because you do end up with thinner hair, or excuse me, less dense, I believe is the correct term, not thin, because I have a friend that's a barber and went to beautician school. So
yeah, you don't want to call somebody's hair thin. That's kind of like a less dense.
It's just less dense. Sounds nicer.
I used to worry a lot about losing my hair until like I barely knew my grandpa on my mom's side, but seeing pictures of him when he was in his 80s, he had like, I mean, just thick hair like this tall. So I don't worry about losing my hair anymore. Although I can see in the camera, the hairline is getting just a little bit farther back there.
It's
But-
just the camera, because I mean, my forehead's not really that big. It's just the camera.
or Lena, I'll take that. I'll take it. I don't know if I believe it, but I'm just going to choose to believe it at this point.
It adds an extra ½ inch to the widow's peaks and or to the forehead.
So that oxidation reduction chemistry, that's definitely something that I might be interested in you talking about on an exam. So make sure that you know how perms work in terms of being able to reduce the disulfides in cysteine and then make new disulfides with different cysteines. That's important because it's one of the coolest places that biochemistry is like super accessible in our society. Most of us don't like conscientiously make decisions that make us do chemical reactions to screw with our biochemistry on a daily basis. I suppose like if you're talking about dosing yourself with drugs, but that's complex. This is really easy to understand. So I think it's pretty neat.
Is there another page in the book that like goes into more depth about that, or?
Really not much more depth than that, but it is talked about in chapter 14.
Okay.
Any more questions? Anything from 14 at all? So the stuff that we had to learn today was mostly like a little bit more nomenclature for ethers, for halides. I had to teach you about nomenclature for thiols. It's in the topical videos for 14 already. It's really easy. So the suffix that we use for the SH group is the ane thiol. So instead of just all, ane thiol is what we use for our suffix when we're talking about an SH group. So this would be 2-butane thiol, for example, the 2 being the locant for the thiol functional group.
I have a quick question, I think.
I might have an answer.
How many hydrogens are around the sulfur, since sulfur is one of those obscure elements that can do multiple, like,
So
more-
that's why you have to write in hydrogens on heteroatoms. There's only one, and you know there's only one because you write in hydrogens on heteroatoms in bond line drawings. So
you could do H4 if there was 4.
but yes, if there were 4, but there aren't. So the way that sulfur works in thiols is essentially, well, it's exactly the same that oxygen works in alcohols. So sulfur has 2 bonds and 2 lone pairs in thiols, the same way that oxygen has 2 bonds and 2 lone pairs in an alcohol. There are times when sulfur can just absolutely thumb its nose at the octet rule. Like,
That's
for
what I was
example,
wondering about.
here, yep, that's what that is. It is a typical case for why you must write in hydrogens when they're attached to heteroatoms. So we wouldn't know off the top of our head what sulfur's chemistry was doing here unless we were explicit about how many hydrogens there were. We know that because there's a hydrogen and a bond to a carbon here, that sulfur's following the octet rule and has a couple of lone pairs on it. All right. Sulfur could also be like this with 6 bonds and no lone pairs. So that is the Lewis structure of the sulfate ion, SO4 2-.
Are we gonna have to deal with that on the test?
No,
Okay.
I'm just, not everybody has had enough chemistry to know how sulfur is an octet rule violator. We're not going to have to worry about sulfur containing compounds that don't follow the octet rule in this class.
Perfect.
All right. The closest we'll get to that is we'll talk about some nucleotide triphosphates, where the phosphates that are attached to a nucleotide don't follow the octet rule. So you've heard of ATP, all right?
Yeah.
Yeah. So in ATP, the phosphoruses also thumb their nose at the octet rule. So you'll have to deal with that when we get there. But files follow the octet rule. All right. Good question.
Okay, thanks.
Any other questions? Anything that you want to do more practice with? Remember, this is supposed to be exam 1 review time. So anything from the first 4 chapters that you could just use a little bit more practice with or want another example of. I like making up examples.
I mean, I wouldn't mind an example of just everything as we go through, just like one of each.
One of every.
Just not like excessive, but like, you know, an alkene and an alkane, and just like kind of.
Are you talking about naming? Or are you talking about reactions, physical properties, polarity?
Yeah. All right.
But that's all. I mean, that's a lot, right? So just with alkenes, we could talk about naming an alkene. We could talk about any one of the, I think, 4-ish reactions of alkenes that you have to know about.
Yeah, never mind.
What?
No, it's not a never mind. Just like, what would you prefer? What kind of problem do you want?
Let me think.
What would get
While you're thinking, why don't we name one together? Name that alkene for me. And then when you're done naming that alkene, tell me what it turns into when we treat it with water and H2SO4. Assume that both of those double bonds react. And after you write your product, name the product as well. So I have this as 3-ethyl, 1-methyl, 1,3-cyclohexadiene.
Yeah.
Now let's remember, what does water do to alkenes when we have a catalyst of H2SO4 with it? We call this hydration. All right. The adult way to talk about that reaction is to call it acid catalyzed hydration. That makes you sound really smart when you say that. All right. So hydration of a double bond means that we're adding an OH to one carbon of the double bond and an H to the other. So how do we tell which goes where?
Well, substituted against the OH.
Yes, that's Markovnikov's rule, stated a slightly different way than I've been stating it for you guys. The way I've been stating it for you guys, Markovnikov's rule is the hydrogen goes to the carbon that already has more hydrogens. All right. So in that case, for this carbon-carbon double bond, the hydrogen would go here and the OH group here. For this carbon-carbon double bond, the hydrogen would go here and the OH would go here. So we would end up with a product that looked like this.
For boiling point for that molecule after it's gone through the hydration reaction, even though it has 2 OH groups on it, it still wouldn't be very
That would be,
polar.
it'd be super polar.
It would be?
Oh,
That
yeah.
would make up the size of the carbons?
What's
The
that?
number of-
Well, for a couple of reasons. So Ariana, the first thing you have to think about is this thing has a total of 9 carbons. So it's getting pretty big in molar mass.
Yeah.
It is
Yeah.
also capable of hydrogen bonding, the strongest type of intermolecular forces. So this thing would have a pretty high boiling point. I would guess its boiling point would probably be something like 240, 250 degrees Celsius. Just a guess, but probably a pretty good one.
So because it's larger, it has more London dispersion and it has the OH groups. So it would do hydrogen
Yes.
bond for those 2.
Yes.
Okay. So the
And on top of that,
non-polar-
it has a pair of groups that are both capable of hydrogen bonding. So that's a pretty big deal. To have the more hydroxyl groups you have, the better at hydrogen bonding you are. So these can form quite a few hydrogen bonds with their buddies.
Okay.
But in general, like, I'm not going to ask you to predict boiling points. I would just ask you which would be higher boiling between these 2 compounds. And you would say that one, right? So it'd be like, you know, slam the B button there. It's not going to be, it's not going to be a hard question. It's going to be a small molecule and a really big molecule. You'll pick the big one to have the higher boiling point. Or you'll have a small one and a big one that have the same boiling point, and you'll have to tell me why. As a matter of fact, that was like the very last question in chapter 12's homework was, I think it was cyclohexene and water have essentially the same boiling point, even though cyclohexene is a lot bigger. Why is that? Well, water is smaller, which means that it should have lower amounts of intermolecular forces, but it is also very polar and capable of hydrogen bonding, which gives it stronger intermolecular forces. So the 2 things sort of offset.
When you put them all together, those are the van der Waal forces, right?
I hate that term.
Okay.
Yes, that's fine.
Okay.
Some people use van der Waals forces as another term to talk about London dispersion forces, and some people use van der Waals forces to talk about intermolecular forces. So
That's
the language is a little bit unclear. Yeah, yeah.
Book used it differently than my last chem class used it, so it was a little.
That's why I try and give you nomenclature that is not
ambiguous.
Right. And I don't really like London dispersion forces as a name either, because it's not a descriptive name. I prefer to talk about intermolecular forces with a name that describes what they are. And London dispersion forces descriptively are induced dipole forces. You're inducing a temporary dipole on each of those nonpolar molecules, and those temporary dipoles are attracting one another. So that's why I prefer that name for them, because it's descriptive. All right, and can anybody name this for me? It's a tough one.
1-ethyl 3-methyl-1,3-cyclohexadiol.
I think it would be 1,3-cyclohexane diol, but otherwise perfect. I would have totally given you full credit for that on a test. All right, so you just truncated the back end of that name a little bit. So if you have a diol, ane diol is the suffix that you'll use, but otherwise perfect. So you alphabetized correctly and counted from this as carbon number 1 because ethyl comes before methyl in the alphabet. Very good. So 1-ethyl, 3-methyl, and then you gave locants to both the OH groups. Again, bravo. 1,3-cyclohexane diol.
Every time I look at those big things, I look at them and I get very intimidated and think, I can't do this. And then I sometimes can and sometimes can't.
That's the cool thing though. If you practice, even really big organic molecules are very nameable, especially ones
Right.
that just have one kind of functional group in them. They're very nameable. Like, you've only been in the class for a few weeks and you're already naming things like this. That's pretty impressive, right? So
I found out that I tend to leave things out.
I don't want to be dismissive, but don't do that. Just don't do that.
Like sometimes I'll forget the cyclo part of it.
Yeah.
I know what I'm looking at, but
The classic thing
Take
that
it on
students
to-
leave out when they haven't been doing it for very long is the cis and trans for cis and trans alkenes. So make sure that if you have an alkene that has two different possibilities for what it could be, depending on whether it was cis or trans, you have to say which one it is. Okay.
Are cis and trans only, do they only affect the enes? They don't affect the anes or the ines?
Yes. There are other kinds of cis trans isomers, but we're not going to talk about them in this class. All right. So for example, this is not something that you need to know, but those two molecules have to be given different names because they're different molecules. We're not going to talk about them in this class that way. I would have you name them like this. I would have you name this as 1,2-dibromocyclohexane. Fine, done. But in reality, as we go on further, that's like a white lie that I just gave you right there by giving you credit for that name, because 1,2-dibromocyclohexane can look like this, where the two bromines are on opposite sides of the ring, or like this, where they're on the same side of the ring. So one way that you can get around that is to call that trans 1,2-dibromocyclohexane and this cis 1,2-dibromocyclohexane. There are other ways of talking about that as well. These are also a pair of stereoisomers. So the only stereoisomers we need to worry about in this class are cis and trans isomers of alkenes. But really, that's just like a little taste of basically a huge can of worms. If you want to open the huge can of worms a little bit more, look in chapter 15. Notice that we're basically skipping chapter 15 for the class. That chapter is stereochemistry. All right. It's just we don't have time with all the other crap we got to do.
Okay. Would that be applicable to an advanced biochemistry class?
Absolutely.
Oh, okay.
So absolutely. The reason why is stereochemistry is incredibly important for how small molecules dock into enzymes. So the
Yeah.
three-dimensional shape of the molecule means it's either going to fit or it's not going to fit an enzyme.
Oh.
Okay.
But there's different levels of applicability too. So learning how to differentiate and name all the different types of stereoisomers is not as important as realizing that three-dimensional shapes of molecules are essential when you're thinking about biochemistry. All right. So we will do that second part, but we're not going to know all of the different possible types of stereoisomers and how to name them. That's too much for this class.
Is handedness part of stereoisomers?
Yes.
Okay.
So as a matter of fact, this molecule, it's probably not even good enough to call this trans 1,2-dibromocyclohexane. And the reason why is because this molecule is not identical to this molecule. So these are the different, if this is the left-hand version of the molecule, this is the right-hand version. These are called a pair of enantiomers. That's all enrichment. You guys don't have to remember any of this stuff that I'm talking about right here at all. That's chapter 15 stuff. Okay, so yes, handedness is very, very important. We will talk about it a little bit when we start talking about amino acids and about other types of biomolecules that have handedness to them as well. All right, but we're just not going to learn how to name all the different types of stereoisomers. It's too much. It's too much.
Okay. Thank you.
Yeah.
I have to do an advanced biochemistry class later as a prereq, so I'm like,
Oh, I'm so sorry.
What course number is it?
well, at that university, it's 381.
So that, do they have a majors level organic chemistry as a prereq for that?
I don't know.
They probably do. So most, because I used to teach junior, senior level biochemistry at the university where I worked before I worked here. Most of them have majors level organic chemistry as a prereq. So the cool thing is, like when you're done with this class, you'll have seen some things from that class, but there's a lot of stuff that you'll have to learn in the majors level organic class. It's really fun. It was my favorite class to teach at my old job.
I don't have to take the whole series is the weird part. Like I have this class and then advanced biochemistry. Those are the only two.
You don't have to take majors level organic chemistry?
No, I just skipped straight to the biochem from this.
There are
What are you going for?
Dietetics. So
What?
it's all about enzymes and vitamins. That stuff.
Oh,
Yeah,
And
I'm very interested in why they wouldn't make you take a majors level organic class for that. But there are a few things where you'll probably have to scramble a little bit.
I should rephrase. The biochemistry class might have prereqs that are outside of the prereqs for the program, where the program requires the advanced bio and this.
Yeah.
So what that class, I'm not certain yet.
The biochem class may have prereqs, so you should look at that very carefully. So most junior, senior level biochemistry classes have organic chem, majors level organic chem as a prereq. They may not have the whole year of organic chem as a prereq, but like maybe a quarter of it at least. So there are some things about how organic molecules react that you're just not going to know enough of when you get done with this class. But if you want to like pop into office hours, if that advanced biochem does not have an organic prereq, I can point you in the direction of the stuff that you are going to be a little bit deficient on when you get in there if you haven't had organic. Okay, I'm happy to do that.
Touched on OChem and AP that decade ago.
Right.
Until you take majors level OChem, like yes, this class is organic and biochemistry. We are literally like the Titanic scraping off a fingernail sized piece of ice from the iceberg. We are not ramming the iceberg. We are scraping a small scraping. So organic chemistry is amazing. I love thinking about the mechanisms of organic reactions and learning about all of the experimental tools that we use in the chemistry lab to identify and purify organic molecules. It's a very rich, complex science. So most, if you look at like master lists of the most difficult undergraduate courses, majors level organic chemistry is almost always top 3 in the list. And physical chemistry, which is a senior level chemistry class, is almost always in the list too. So chemists just get like destroyed in undergrad. We have really hard classes. I'm not trying to scare you away from chemistry. On the flip side of those being very hard, they're also incredibly rewarding and bring you to like a very deep understanding of how things in the world work. But they're both very information heavy classes. I don't want to do that. draw the correct product of this reaction. This is one of those reactions of alcohols. So if you're just reading in the book, you're probably not going to see this reagent anyplace. It's in my topical notes from chapter 14. It is also in recitations. We've talked about it a little bit. So this is an oxidizing agent that has a very specific fun activity. It reacts with alcohols a little bit differently than most oxidizing agents do. So this is a great example because it reminds us of the chemistry of both primary alcohols and secondary alcohols when we oxidize them. So PCC is interesting because it oxidizes primary alcohols only until they become aldehydes, and it doesn't go any farther than that. Jones reagent oxidizes primary alcohols all the way until they are carboxylic acids. So you can see the difference and the similarities between them in this example because PCC and Jones reagent do exactly the same thing to secondary alcohols. They turn them into ketones. And honestly, like that would be a great example of a potential test question. Like draw the product of that reaction. Or draw the product of that reaction. Or draw the products of both these reactions. And it'd be a 2-point question or something instead of a 1. So drawing products of reactions, just like we've done in pre-labs or in class or in the notes, that's definitely fair game for the reactions that we've learned so far. Naming simple compounds, fair game for the the classes of compounds that we've learned so far. Essay questions where we talk about types of intermolecular forces or shape or bond angles. Like that's the stuff that we've done so far in the class. Also, let me remind you that even though you don't have a practice exam yet, which you will soon, all right? Where did it go? Where'd my book go? Where is my book? I might have taken it downstairs. Okay, so I'll just have to tell you in words instead of showing you. At the end of each chapter, there is a chapter summary that contains important terms. Review of the reactions that you've learned in the chapter, I think. All right. So the last page before you get to the assignment for each chapter, there's a review that talks about all the most important concepts. That's a great place to start your studies. Are you familiar with all of those key concepts from chapters 11 through 14 at this point? All right. So you've got like a week and a day left to study. that's a long time, but if you're not comfortable with something, don't like wait until Monday night and then text me about it at 9 at night. I probably won't have time to help fix it then. So I have office hours Tuesday, Wednesday, Thursday this week. Stop by, ask me to do a couple of extra problems with you if you're not sure about something from one of the homework assignments. I'm also going to publish keys for the homeworks that we've already turned in. So there were a couple of students that had good reasons to have extensions, but those extensions are done for them now. So I can publish the keys so that you guys can go back and compare your answers on the homework to the real right answers. Make sure that you do that, because I don't have time to like analytically pick apart all of those homework assignments. There were some pretty bad answers in some of them. So make sure that you go back and look over your questions to see what you got wrong and what you can learn from the right answers.
Okay.
Anything more? We've been at it an hour and a half. I don't want to take a break and like come back for a half hour. Let's just be done for the night.
Okay.
Thank
All right.
you.
Sounds good.
Have a wonderful night. I'll see you guys on Wednesday.
Wait. How did your weekend go? Like,
What do you mean my weekend?
well, like, I mean, from the news that you gave us on Wednesday, like,
I'm not doing great. Yeah.
Yeah.
I mean, honestly, I'll probably be a wreck for a couple of months. My cat was amazing. He was my best buddy. So
yeah.
I'm floating. I feel a little numb, honestly, which is not good.
Yeah. All
I'm
right. Well, figured I'd ask, maybe.
Yeah,
see
I
if-
appreciate that. I'm
for
fine.
sure.
I'm fine. So it just, yeah, it sucks. He was my buddy. He was my
Yeah.
co-instructor too. He would always meow and come up and hang out with us when we were teaching. So yeah,
Yeah. All right. Well, have a good night. Thank you.
thanks, Orlina. Have a good night, everybody.